Welcome to another episode of Code for Thought. In 2022, I had the pleasure of talking to Simon Pinches, section leader for plasma modeling and analysis at the international organization called ITER. ITER stands for International Thermonuclear Energy Reactor, or if you prefer Latin, for the path. It is a large international collaboration which tries to show that nuclear fusion can be used as a future energy source. Back in 2022, I planned to meet Simon on site at the ITER offices in Cadarache in the south of France. But for a cancelled train and a bout of gastric flu, it sadly didn't come to pass. I was all the more pleased and excited to make up for it this year and finally meet Simon and his colleague Olivier Hoenen in person. And so, on a sunny and hot morning in late June 2023, I made my way to ITER, altogether a 1-hour bus journey from Aix-en-Provence, a journey which took me through a stunning and dramatic landscape. Simon and Olivier welcomed me in the ITER main office building, but before we began with the interview, they very kindly gave me a tour through the site, and what an impressive tour that was. In the main building where the reactor is housed, we saw 2 segments of the donut-shaped reactor called tokamak being assembled, one being held upright and the other one still lying face down. At the time of the visit, one segment was already in its place. The sheer scale and complexity of the operation as well as the size of the reactor components took quite frankly my breath away. This is of course not the first tokamak to be built. There have been others, most notably the Jet tokamak in Oxfordshire in the UK, which broke the record for energy production in 2022. But ITER will be a different beast altogether. When ready, it'll be the largest tokamak reactor built with a core temperature 10 times the core temperature of the Sun. It will be a test reactor to demonstrate that nuclear fusion can be a viable source of energy production and the design can be used for future power stations. Simon and Olivier were excellent tour guides. Apart from the Toro segments, they've also shown me other essential components that await assembly. After about an hour, we arrived back at the office to sit down, and it was at this point that our conversation started. So now over to Simon and Olivier. Hello, Simon.
Hello, Peter again. Good to see you in person this time.
and in person, exactly. Yeah, and we recognized each other sort of straight away. Well, that was a very impressive sight. So we saw one segment being held up.
Yes.
And the other one lying down.
Yes.
In the assembly hall. And I think one is already in place.
That's correct, yes. There was another sector of the machine that was in the pit, which unfortunately we couldn't see today because of the work that was going on there. But yeah, we saw 2. One in the subsector assembly tool where it will be assembled together with the other components before it also gets eventually lifted into the pit, and another one lying on its side in preparation for being assembled.
We're getting a little bit ahead of ourselves, but I know that we talked to each other last year, but maybe you can quickly introduce yourself.
Sure. So yes, I'm Simon Pinches. I'm the section leader for the plasma modeling and analysis section here in ITER within the science division. And our primary goals are to prepare all the software that will predict what will happen inside ITER in the future, to guide the preparation for all the experiments that we've done, as well as to prepare all the tools to interpret all the measurement data that we get out to really understand what's happening inside this machine and how we can tune it and improve what we're doing to achieve the ultimate goal of producing lots more energy than we put into the plasma, shall we say, yes.
Indeed. And with us here today is also Olivier.
Hi, nice to meet you. I'm Olivier Hoenen. I'm working here at ITER on the science division, so in the same section that Simon. And here at ITER, I'm managing the development or the infrastructure development of IMAS, which is the name we gave to our software infrastructure or our platform that will be used for preparation of the shots and also analysis of the data that is coming out of ITER.
And you've been working for how long at ITER?
I arrived at ITER this summer. It will be 3 years. So I arrived just in the middle of the pandemics, summer 2020. And yeah, it's been a lot of things to do and a lot of new skills to learn since I arrived there.
Are you also a physicist?
I'm not a physicist. I'm a computer scientist. I did my PhD in informatics, as we call that in France, in Strasbourg. During my PhD, I was directly working with mathematicians and physicists because the codes that I was working on, semi-Lagrangian codes, and my whole studies were about to porting them efficiently and working on load balancing for parallel codes, MPI codes, which were big at that time, but nowadays, when you look at number of processes and cores that we were dealing back then, it's laughable. But still, back then the idea was more like to work on algorithm and smart adaptive methods to reduce the number of computation to be made. Nowadays, this goes more in the other direction. We try to do things a bit more brute force, still smart decomposition, but not really adaptive grids and a lot of things like that. Since my PhD, I would say I started to interface a lot with other communities, physicists in plasma science. And that's where I came into this first Europe fusion community. And then I ended up in working at ITER.
And I think we will be talking about how people could spend some time in ITER, maybe a little bit later. But back to ITER, because the software that you look at, it's not only used for when ITER is running, it's actually putting things into place and trying to herd the cats on a technological level.
It's an interesting description. We want to assemble the software to do the best possible predictions of what will happen in ITER. And we don't want to wait until ITER operations start. So we're writing all the software in a way that it's not just specific to ITER. It can be used, tested, validated on today's machines. And this is really important, especially as we're forever looking at how we can optimize the research plan for ITER to go faster. This is going to allow less time between when we first get some data out and we want to start really using it to refine what we're doing. We don't want to then, it doesn't work. What should we do now? Well, let's go and have a think about writing another code. No, we want to have tested it on many different tokamaks today. So ITER's a tokamak, this donut-shaped machine. We want to test it on as many machines to which it's as applicable as possible to have the greatest experience, not just that the codes work, but also that there are people who know how to use the codes who can actually come here and help us in the future. We're not that big a team within the science division, and having people with the skills for the future is important to make sure we'll be in a position to capitalize on all this big investment we're making in terms of bits of metal that you looked at today, and buildings and pipes and trenches and everything else we saw here. Yeah, we want to put together all this software, but do it in a way, this is why it's integrated modeling. We're putting together models that previously were maybe used in isolation, but we're not just going to describe what's happening at the edges of our plasma. We want to do it in a clever coupled way that we're simultaneously describing what's happening in the middle of the plasma, what's happening when the plasma touches the wall, what's happening to the wall material, or elements from the wall coming into the plasma. How does that affect the plasma performance? Some energy is radiated. Maybe it affects the stability of the plasma. We want to model the control system, which is reacting to these measurements. So we need modeling of the measurements, which means we need diagnostic models, or so-called synthetic diagnostics. ITER has something like 40 different diagnostic systems. So this is 40 different models, at least, for those systems, all of which are not new. These, in terms of those diagnostic techniques, are used today. So if we build models for these diagnostics, we could test them today, either in isolation, just to say, well, if your plasma's like that, you should measure this. Do you? Compare it with our model. Yes. Oh, that's great. Now I have more confidence in this model. And then you can go beyond that and use it within your simulations to kind of think about doing controlled feedback on your synthetic diagnostics, as sometimes they're called.
I mean, the reason why I'm referring to it as herding cats is because when we look at the massive building side, there are so many components that need to come together. Maybe a herding cat is really the wrong metaphor. Maybe it's more like a ballet, where sort of every dancer moves in a defined
Maybe it's more like an orchestra, yes? You need a conductor who's going to conduct it all together and bring it together to hit the right note, shall we say, yes? So it's true. We need to... Well, first of all, we obviously need to assemble the machine. And even as part of the assembly process, there's lots of modeling that we can do to say, what if there are slight uncertainties on where we put the magnetic field coils? What effect does that have on the magnetic field? What effect does that have on how good the plasma now confines energy or confines particles? So how accurate do we have to be? So these are all questions that we've looked into and are looking into and are using our knowledge to guide the installation process in a way, and how accurate various bits and pieces need to be put together. So yes, it's a very complicated process involving lots and lots of different people, the engineers who are doing it, planners, managers, software engineers, physicists. There's room for everyone to get involved, and lots of different people are involved.
I would imagine so, yeah. Because I think, Olivier, you are kind of modeling some of that, aren't you?
So not doing the modeling myself. Basically, I'm preparing the whole software infrastructure that will help physicists to do the modeling. My job is really to orchestrate a bit all the software and how they integrate on the computers to help people doing modeling in a sense that many of the models can talk to each other. So our ideas is, and that's something that is historically a bit missing in the fusion community, is to promote and to develop, first of all, a sort of data standard that can be used for our community. And of course, when you develop the data standard, you need to make sure that the standard is useful for the various part of the physics and for the various modelers that will develop the physics codes. And so there is a lot of discussions and iterations with the physicists, with the modelers. You need to be careful also and take care of the implication in terms of the implementation. This platform, we call that IMAS, the Integrated Modeling and Analysis Suite. And the core of it is really this data model. We are trying to promote that as really a standard. There are still a few steps ahead to really have what we could call a fair data standard, but we are actively working on that aspect.
Fair in sense of findable, accessible, interoperable,
yes,
and reproducible.
Exactly.
Okay. I remember that we talked about IMAS last year. At what stage is it now?
I think Olivier's best placed to answer that question, but it's getting better and better all the time, as I'm sure he'll tell you.
Well, no, it's becoming very interesting and challenging because we are about to release a lot of major new versions of various bits and pieces. So we have, as I told you, the data model, what we call the data dictionary. We are working on a new major version, which is this big bump where we allow sort of backward incompatibilities to be implemented. And together with that, we have also the data model is one thing, but then if you just have a dictionary of data structures and how you should formalize the data, that's still a lot of work on the physicist at the end, and we want to help there too. So because we want to have that as a standard, we also want to have standard tools to help manipulating these types of data. So we have tools to store and access the data, and that we provide interface in most of the languages, programming languages that are used in the community.
Like?
Python, Fortran. Well, let's start with Fortran because Fortran is still a major thing in the community. C++, Python, MATLAB, and Java. Once we have access to the data in any of these languages, we have also tools for doing visualization of the data, to organize databases, various zoo of standard tools that allows to develop applications. And applications, physics applications, are really the final target of what we want to have in IMAS.
You mentioned stumbling blocks with regards to the data model and the standardization. Could you describe what they are?
So we have a sort of ontology where we try to separate concepts, like either part of the physics or maybe part of the tokamak of what you saw. Simon mentioned that there will be 40 different types of diagnostics. So for all types of diagnostics or some part of the diagnostics, because there are many diagnostics that look a bit alike based on cameras, various technologies. So we have data structures, what we call IDSs or interface data structures, that are trying to catch all the meaningful information to describe if it's a physical device, how the physical device is installed and where it looks into the plasma, and what are the data that are being captured by these diagnostics. And we have also data structures that are more on the modeling and the simulation part, where we can describe the turbulence, the core profiles, so the density profiles inside the plasma or at the edge of the plasma, the MHD phenomena, and various kind of things. And we have yet another categories of data structures that are there for bookkeeping, for storing numerics, for storing provenance, and things that will help us to make sense of the data in many years, and also to help to reproduce the results and the processing chain that will be applied on the data.
You mentioned fair, and the A stands for accessible. How accessible is IMAS and the system?
That's a good question. So it's obviously accessible to all the ITER members. So the 7 ITER members, the European Union, China, India, Japan, Korea, Russian Federation, the USA, they all have access because we're all equal partners working together to realize ITER. And by themselves, they represent about half the world's population. But actually, we want to go beyond that, and we're really pushing to try and make the core infrastructure that Olivier was just outlining open source. Now, it contains some background intellectual properties from within the ITER members, but we're optimistic and hopeful that we can make it truly open source. And this will go a long way then to making it much more accessible. A lot of the other secondary bits of technology that we use within it are already open source. So by really opening it up, we hope we can make a standard that's really usable by everyone. It's not, even if ITER is a very large number of people, it would be great if it was really truly open source. And it already removes barriers for people who are eligible to have it. If they can just quickly get it off GitHub or somewhere, it's much easier than having to get an account on our systems and get it from there, even if they're eligible to get it.
That's quite an exciting development, because I do remember that from the last year's discussion. We talked about that, yes, the ITER members have access to it, but so far no one else.
Correct, yeah.
It's good to see that you're actually moving more into an open source. Is there anything that happened between the discussion we had last year and now that kind of pushed this along a little bit?
Well, we had some preliminary discussions with some of the people who hold the background IP, and we have background intellectual property, and we think they're going to be amenable to us ultimately making it open source. So, yeah, this helps, yes. If they'd said no, then that would have been a problem.
Okay.
So, yeah, we're moving in the right direction. Of course, that's the infrastructure. Then it's a mixed bag as to whether the physics tools are open source. A lot of the tools that Olivier talked about that we're adapting, they've been written over a very long time within the fusion community in all sorts of different guises by different laboratories and research groups, and how they license their physics tools varies enormously. And probably very few of them actually have any kind of formal license agreement associated with them. They will claim things, but if you actually ask a lawyer, then it all gets very difficult. But a lot of tools are moving in the right direction, so I can see a significant amount being made open source ultimately, and I think this will help then to make more and more open source. Of course, it's not just open source. Really, it would be great to have open data as well, because then we can openly test the software on data. And some machines around the world within ITER members have got policies in place, and I think this is going to be something very interesting for us to explore. So we can put together software with some examples from different machines, and we can really help validate the tools on real data and see that it works in preparation for when we need them to work on ITER.
And also make it more reproducible, which of course
absolutely, yeah. So Olivier already mentioned about the capturing the provenance information within the data model. We don't just want to know that you used code X. What version of code X? And do I have access to that version of code X? So is it really reproducible? On the experiment, we like to think science is reproducible, but actually once we get to the software level, it really should be reproducible.
Yes, so indeed, exactly, yeah. Because a lot of the science is also actually developed with the software.
Yes, absolutely. We're kind of capturing all our physical and scientific knowledge in these little models. So everything we know is captured in these models, and we want to continually test and update and know where they work and know when they don't work and know when we can trust them in ITER for that reason, yes.
So in a year's time when we talk about this again, do you think that it might be open source then? Do you think
I think it might be open source then, yes. Let's be optimistic. I would hope so, yeah.
The other subject that I wanted to touch on and that we started talking about is that there's obviously a huge amount of work to be done. And in the cafeteria, before we went on this walkabout, we had a little bit of a discussion about how people can get involved and how they could maybe spend some time here at ITER. Could you perhaps expound on that for anybody who might be interested in joining that?
Yeah, sure. Well, there's many different ways that people do already contribute and can contribute. So for people working within the sort of like fusion research environment, probably their laboratory already has some kind of relationship with ITER. And we have various mechanisms, topical groups and things where they can get directly involved. But in general, and particularly when it sort of like crosses over from the physics science area, which really links all these fusion labs together into the more general software area, then there are, and I'm sure there are many people doing relevant similar work in other fields whose skills would be very valuable to us. And there are various mechanisms and ways for people to come. Of course, people can always come as visiting researchers, where literally we would provide them with a desk and agree a work plan and they would come, but this would be all at their expense, so there's probably not so many of them. But there's also more like secondment type schemes like the ITER project associate schemes, where people working for so-called home institutes, so labs, universities, wherever, can stay working for their lab, but then come to ITER for a period of time, maybe up to several years, 4 years maybe. And for that, then we would be able to provide some kind of allowance for obviously they've relocated to another country and come here, and also reimburse to some degree their institute who would have sent people here.
As a UCL person, I could convince my boss at UCL to send me to ITER, and you would pay kind of allowance, and UCL would get reimbursed for that period.
Correct, yes. I mean, this also needs to align with a need from the ITER side, but we have regularly made adverts for ITER Project Associates. We have one at the moment, another one shortly to arrive, who will work here and be based here all the time, and live in Manosque and send their children to the international school and whatnot, and help us build these things. It's really good to make contact with people from other fields, because they bring in knowledge and expertise that we don't necessarily have. I mean, we're quite a small team. The whole science division is probably just over 30-something people, and within our section there's...
And that includes you? Or?
Yeah, that includes... Actually, that's not just us. We're half of that, so we're probably down at like 15 to 20 people, which sounds quite a lot, but there's no overlapping skills. Sort of like everyone has got their own job to do individually. So extra support people to help us building and assembling things is very useful, yeah.
And if people are interested, where can they go?
They can always write to us if they can find our email addresses. I guess a quick Google will find us on somewhere or other. Or you can look on the ITER website, www.iter.org. Under jobs, you will find IPA adverts. And there's also a description of the scheme there as well, where there's more details on how it works and how they would apply and whatnot.
But it doesn't apply for people if I were, for instance, unemployed or don't have a job and I'm looking for a job.
Then you could apply for a job.
yeah, but it wouldn't go for
But there's not so many jobs. So the ITER organisation, we have a capped fixed number of jobs that we're allowed to have, that the ITER members allowed the ITER organisation in its responsibility of pulling out all the different things from all the different ITER members to come. There's a fixed number of jobs. The easiest way to contribute would be, at the moment, for our line of work, would be through the ITER Project Associate Scheme, yeah.
The other subject that I would like to talk about is what's it like to work at ITER? There are 7 different organizations, large organizations. There's the European Union with all its 26 members. It used to be 27, or was it 28 and it's now 27? But anyway, so there's the European Union, there's India, there is China, there's the Russian Federation, there's the US and Korea and Japan. That's quite an international community, isn't it? And I think the territory in which we sit right now is actually not France, is it?
This is like international territory, yes.
I mean, working with all these different countries, how complicated is it actually in the day-to-day life? And how would you describe that?
I would say for most of the time, we don't really think of people's different backgrounds. I would say we're pretty integrated. It's not that all the different nationalities sit separately at lunch or do their own things. I mean, occasionally there is a certain national day in the canteen where we all have food from one of the ITER members, which is very nice and maybe doesn't happen as much as it used to do. By and large, I would say we're all pretty well integrated. I mean, for new arrivals on site, I know the Welcome Office offers intercultural experiences and training and things. Of course, we're all living in France, and so depending on your cultural background, it might be more or less of a shock to come and live in another culture, but that's more outside work. And of course, then there's the international school as well, where people can send their children, and then they get a mixture of potentially their home culture plus then French local culture. Yeah, I don't know. Do you want to add anything specifically on the...
I cannot tell much about the outside work because I'm French myself, so I know I had a bit of hard time because it's south of France and
you're from Strasbourg,
yes,
aren't you?
Yes. So there is sort of more difference from me getting here than me working in Germany the years before. So that needs adaptation, but the region is gorgeous, so it's always easier to adapt to a place like that. But I think at work, it's also really rewarding to work in such multicultural environment because you learn a lot by just on a daily basis, discussing, exchanging, trying to compromise with people of very different background, different countries. So it's not just the countries. I mean, I'm a computer scientist, I'm working with physicists, There are like software engineers that are coming from the industry. I'm coming from the university, and so I really don't do the same software and software engineering that people that are coming from industry. And so there are a lot of different skills, mindset, and you have to learn how to properly interact. That takes some time, especially each time you have to interface with a different section that have really a different job, and you don't know all the acronyms. There are a lot of acronyms here. It's not just the language, it's also the culture and the background. Yeah. But at the end, it's very rewarding to just find ways. That's what I've always been done throughout my studies and careers, being at the interface and trying to find ways to communicate and speak the same language, because that's the most difficult thing, right? Is to understand each other when you're not speaking the same language in terms of your ideas, even sometimes in the mother tongue.
It's a little bit like CERN in the sense that you have to interact when you talk about interaction. It's between physicists and software engineers, but then there is also the hardware engineers, the people who build the electronics, the people who actually assemble the whole thing. So how is that working then, the communication?
You're not always interfacing or discussing directly with all the people. I mean, there are so many people on site doing so many different things. But yeah, every now and then you're discussing with someone that is doing something slightly different than you, and that helps you understand somebody discussing with that is doing something even different than him or her. And so you're trying to build a chain like that of translations of concepts and understanding what's the words that helps understand each other. And then you hope that throughout this chain, your ideas at the end are well received. And then because you're trying also to follow each translation steps through this chain, it also helps you to then build different mindset or languages that will, at the end, you will be able maybe to discuss very efficiently directly with the person on the other side of the chain. But it takes some time. And of course, it takes some effort to do that properly.
Simon, you've been here since 2012, haven't you?
Correct, yes.
And it looked very different then, didn't it?
It did, yes. We were next door. The building didn't exist, and there was no building on the work site either, yes. It's changed a lot.
It's changed a lot. So you were there more or less, not from the beginning of ITER, because I think ITER, the organization, is... You mentioned during the times of Reagan and Gorbachev, when it was?
That was when they first signed the agreement in 1984. But ITER organization, I think, started in about 2006. So even though they'd agreed, it took quite a long time before everyone agreed. And then the ITER organization was set up. And then, so I came in 2012 when I guess it had existed for 6 years. And we were next door on the CEA site in Portakabins. And this was a big, rough area of land that was cleared and, eventually turned into what you see today, which is quite a big transition.
It is quite a big transition, and sort of that must have been very pleasing for you then to see that.
I can definitely see progress, and probably you will as well if you come back again. Yeah, no, it is in that sense very nice to see the project advancing and going from a concept, an idea, to tangible reality where you really see not just, first come buildings, and then they're not just empty buildings. Now you really see things in these buildings, like significant, impressive pieces of equipment like we saw today, the vacuum vessel sectors with the toroidal field coils and the thermal shields. And
so how far away are we then from the assembly? Is that difficult to say? I'm sure there
assembly in some ways has started. You've seen the components go.
The completion of it, I mean.
Yeah, this is an open question because there are some hiccups along the way. There are some small deformations that need to be corrected in some of the components. So exactly how long it will take for the final assembly is not really known, other than, of course, we all attempt to help achieve this as soon as possible. But it's kind of like the open question that everyone wants to know the answer to, and actually we just don't know at the moment, yes.
Well, we talked about it last year already, that cold fusion is... I mean, it's already been done as test reactors, tokamaks already?
Tokamaks exist, yeah. There's a big tokamak in Oxfordshire, the Joint European Torus, operated by Europe. That's not so long ago broken all the world records, so it's produced the most energy from deuterium-tritium fusion, so the easiest type of fusion, and the same type that we plan to do here at ITER using heavy hydrogen and heavy hydrogen. Yeah, and that's kind of like the only operating tokamak at the moment that's capable of doing that, and then ITER will take on the mantle and lift the torch and carry on into the future and really take it beyond that and get more energy out of the plasma than we actually put in, so show a net energy gain. But in terms of the physics processes, they've been explored as far as was possible in today's machines. Sure, of course, there's new physics that we will explore in ITER. So at the moment, still in JET, the plasma was dominantly heated by external heating mechanisms that we were using to heat the plasma. But what we really want is the plasma to start heat itself. Yeah, this is the bit that's going to make the plasma start burning, if you like. We will put a bit of heat to it, and it will start heating itself and generating their net energy, which we can then turn into electricity, which is something that ITER won't do, but we want to show sufficiently progress in the science and technology that then the world could go out, or so all ITER members can go out and build their own demonstration power stations based around fusion. And that's really the ultimate goal. That's the job that ITER has to do, to provide this final step before you make electricity producing power stations.
And I think the optimists were saying that this could perhaps happen sometime in the next decade or so.
I think the next decade is definitely what the optimists would be saying. I think it might be a bit longer than that, but yes. Yeah. By the time we get into the 2030s, we should be making significant progress, which I suppose is the next decade, yes.
Coming back to this year, what's the plan for this year?
Good question. Well, as Olivier said, we're going to make lots of new releases of things that should open the doors for making advancements in the sorts of like scientific and workflows that we want to build. We want to do lots more validation of the tools that we've already assembled. We've started exploring different ways of putting together our physics components into workflow. We've looked at more advanced ways of coupling the codes together, which will allow them to potentially run in more efficient ways than maybe it would have done if we just made simple imperative Python scripts that called them one after the other. So we want to start exploring those. I mentioned about all the synthetic diagnostics, so these models that will produce data that looks like the data we will produce from ITER in the end. So we want to we have nearly 1,000 predictive simulations that we've made for ITER about what we think the ITER plasma will look like in many of the different scenarios we expect to encounter as we work our way through the research plan towards these goals of generating 10 times more power out than we put in. So we can use those now with these diagnostics models to really start producing lots of synthetic experimental data, which, going back to what we were saying before about working from people from other sections or organizations, we can give it to them. They can put it upstream as if it's been captured off digitizers in the plant, and then we can follow the whole chain down, really doing all the different bits until we get it out, process it as fast as we can, and make our so-called live displays, which would appear in the control room that we just walked past. And so we can test all of that now and see how good are we? Have we sized the computers properly for what we plan to do? Can we keep up with the data rates? Are the networks ready? All these kind of things. So crossing not just the physics applications and the processing, but really trying to put the whole chain in place with everyone in it from start to finish. So first digitizing a bit on a ADC somewhere next to the plant, producing numbers where I tell you a physics parameter, namely what is the temperature in the middle of the plasma. So we want to do that. We continually want to be refining our abilities to predict what's inside the ITER plasmas in the future. So we are continually working on something we call our high-fidelity plasma simulator. And here we've worked at building together different models to capture the different elements of the physics that we think are very important. And we've looked at various different coupling schemes. And then there's also work going on a more simpler plasma simulator, which will be used more interactively. So these very complicated high-fidelity simulators I just mentioned could take weeks to run for one case. So you can't possibly imagine someone interactively doing anything with that on that kind of timescale. So we have also simulators which run much, much more quickly, and they can be used by people really designing a specific plasma. So you can choose the shape of the plasma, where it should be, how much current, and it will then calculate all the currents that need to go in the coils that shape the plasma. It can immediately tell, are you exceeding any of the force limits on the coils, because all these currents interact with the fields to produce forces. There are limits on the power supply, so we can do all of those checks and things. So we'll work on this year, and hopefully next year then we'll be in a position where we can start to make these available to people to start testing on their tokamaks. And Whether they work or don't work, all the feedback is going to be good and useful, and we will continue to refine them, ready for then when we really need these tools. So they're kind of the two different approaches that we're trying to push forward right at this minute.
Thank you very much for your time. I can't thank you enough. It was really exciting visit today, and a beautiful countryside, as you both said. I really envy you living here. I mean, it's...
Well, you came on a good day. The weather hasn't been like this recently. It's been torrential rain for the last few weeks.
But thank you very much for your time today. Yeah. Much appreciated.
You're very welcome.
You're welcome.
Work on using nuclear fusion as an effective and clean energy source has been going on for some time. The concept was developed as early as the 1950s in the former Soviet Union. The word itself is a Russian acronym which means toroidal chamber with magnetic coils. Tokamaks have been built before, not least a record-breaking one in the UK, as I mentioned at the start. Tokamaks, however, are not the only design for achieving nuclear fusion. The Lawrence Livermore National Lab in the US reported a breakthrough with its National Ignition Facility in late 2022 using lasers. Together with a reported breakthrough in the energy production in the jet reactor in the same year, it has led to nuclear fusion moving back into the focus as a source of future energy production. And maybe this time the future is not too far away. Oh, time's up. See you next time. But before I forget, this podcast is covered by the Creative Commons license. See ya.